Here I want to determine the equation for the escape velocity. The escape velocity is the minimum velocity at which you need to shoot a mass from the surface of the Earth so that it escapes the gravitational field. Okay. So we'll determine a differential equation that allows us to compute that velocity. The only force of interest to us here is the gravitational force. The gravitational force now will depend on the distance to the Earth following an inverse square law. So let's recall what the gravitational force is and write down the equation. So we write down the equation for F equals ma. So we have the mass times the acceleration, which I can write as dv dt, is equal to, so we're looking at the F equals ma on this mass here, is equal to the force, which is in the negative x direction, defining x to be up, so it's negative. And then it's the, if you recall Newton's law of universal gravitation, it will be Newton's constant times the mass of the projectile being shot times the mass of the Earth divided by the distance squared between the projectile and what turns out to be the center of the Earth. So what Newton showed was that if the Earth is a spherical object, which is a reasonable approximation, then you can treat the mass of the Earth as if it was being localized at its center. That requires doing an integral over all the little masses of the Earth and summing up all the forces. So we won't do that here, but that's a well-known result. So it's the distance from the mass to the center of the Earth, which here will be, assuming the mass is on the x-axis, though I drew it a little bit off, will be the distance to the surface of the Earth plus the distance then to the center of the Earth. So the center of the Earth is the radius, distance to the center of the Earth is the radius, plus the distance to the surface is how we define x, and the inverse square law says this is a squared. Okay. So this is the differential equation to be solved. The initial condition will be zero velocity initially, or at x equals 0 when x equals 0. So we'll have to see how to specify that condition in a moment. The problem with this equation in the current form is that on the left-hand side we've assumed the velocity is a function of time, so t is the independent variable. On the right-hand side we have the position of the mass, x, which is also a function of time. So we cannot solve this equation because t is the independent variable, and then we have an x, which is a function of t, and a v, which is a function of t. So it's not a single variable ODE. So it's a problem. There's a trick to that, which is to change variables in that we write the velocity of the mass, rather than to be a function of time, we write the velocity of the mass to be a function of position, right? So everywhere that you shoot the mass, as it moves up, it slows down, but it has a velocity at every point x on the way up before it escapes. So the velocity can be written as a function of position, which itself is a function of time. Okay? And then using a chain rule, we have dv dt then is dv dx times dx dt. dx dt, the change in position of the mass as a function of time, dx dt, is just the velocity of the mass. So dx dt is the velocity, and then we have a dv dx. So this change of variables formula is very useful to us, because then we can write our Newton's equation. Remember, we cancel m, right? We can replace dv dt by v dv dx, and that's equal to minus g m, and then I will factor out an r squared, so r squared times a 1 plus x over r squared. Okay? And we can simplify this because we know that the gravitational acceleration, right, this is the acceleration of the mass. The gravitational acceleration on the Earth's surface is minus little g. That's when x equals 0. So that minus big G times the mass of the Earth divided by the radius squared of the Earth is what we call little g. So this one we can write as minus little g over 1 plus x over r squared. Okay, so little g is, as always, 9.8 meters per second squared. Okay? We still need to know the radius of the Earth, however. Okay, so that becomes our differential equation for the velocity of this mass as a function of position. So let me write that down here. So v dv dx equals minus g over 1 plus x over r squared. And then we have an initial condition where we're shooting the mass from the surface of the Earth up. So at the surface of the Earth, the velocity of the mass will be our initial velocity, v naught. Okay? So we have v at x equals 0 is our v naught. Okay? So that gives us our differential equation. It's a nonlinear equation, but it's separable. So we can solve it. We can separate. So we will separate. So we have v dv equals minus g dx over 1 plus x over r squared. And then we integrate from x equals 0 to x. And at x equals 0, we have our initial velocity, and we integrate up to v. Okay? The left-hand side is easy to do. 1/2 v squared minus 1/2 v naught squared. The right-hand side we can do by a substitution. We can let u equals 1 plus x over r. So du is dx over r. So in order to get a dx over r, we can divide through by r and multiply by r, right? So we'll end up with 1/2 v squared minus 1/2 v naught squared on the left-hand side, and minus gr times the integral when x equals 0, u equals 1, and the upper limit is 1 plus x over r. And then we have a du over u squared. this is minus GR. So U squared becomes a minus 1 over U, right? So that minus cancels this minus. And then we have a 1 over U, evaluated from 1 to 1 plus x over r. So that gives us GR times 1 over 1 plus x over r minus 1, which is GR times 1 minus x over r, so minus x over r over 1 plus x over r, right? So the r cancels, and then we can multiply by r, so we have a minus g r x over r plus x. All right. So what this equation is telling us is that the left-hand side is essentially the change in the kinetic energy divided by m, and then the right-hand side is actually the change in the potential energy. So this is a conservation law for energy. The kinetic energy plus the potential energy is a constant. Okay, so how do we find the escape velocity? So the escape velocity is such that v naught is equal to VE, the escape velocity, right? When v of x goes exactly to 0 as x goes to infinity. Okay, so the minimum velocity required to escape the gravitational force occurs when you shoot the object from the Earth's surface at just at the velocity where it goes up and slows down and doesn't ever exactly stop, okay, but it goes to 0 as x goes to infinity. If it stopped before x goes to infinity, it will fall back to the surface of the Earth. If it has some non-zero velocity as x goes to infinity, then you've shot it with an initial velocity larger than the escape velocity. Okay, so then using this result, so we take the limit as x goes to infinity of the equation, right? So as x goes to infinity, v goes to 0 for the escape velocity. So we have minus 1/2 the escape velocity squared is equal to, as x goes to infinity, then r is negligible with respect to x, so we can neglect r, so we get an x here. That cancels the x in the numerator, so we get a minus gr. So we get the formula for the escape velocity is equal to the square root of 2gr, and that's the result for the escape velocity. And if you put in the radius of the Earth, you get 40,000 kilometers per hour, a significant velocity.